Hey there! In this lecture, we're going to discuss inferential statistics, which is another branch of statistics. We have already seen the descriptive statistics and the different theorems and concepts in it, and how we can use it to describe our data in a much better way. Later on, when we will be talking about machine learning, you will see that descriptive statistics is one of the most important and useful tools for a data scientist, especially when he is doing exploratory data analysis. When he is exploring the data, he's cleaning the data in, then he will understand that descriptive statistics will ultimately enable him to gather more understanding, more insights. He will be able to extract more information from the data. So in this lecture, we're going to see another type of statistics which deals with inferring conclusions, inferring insights based on a sample data set, and we're going to generalize those insights to the population. So the population, we're talking about a larger data set, a big pool of millions of data. So it's highly impractical and not possible for any statistician or data scientist to collect the data and then process it. So what we do is we take a sample, a random sample from the population, and on that we perform the operations and we try to learn from that random sample. So, and then we infer our learning to the generalized population. We need to make sure whenever we are drawing the sample's population, it has to be random. Well, the thing is, whenever we are experimenting, we need to keep all other factors constant. Let's look at an example to better understand the random sampling of the population dataset. So, if you want to conduct a survey of, let's say, people who are studying computer science all across the different universities in America, and you want to find out how many of those students have a CS or computer science background, how many of them have already studied a couple of programming languages, how many of them had the aspiration to become a computer scientist. So for that, you have two ways. Firstly, you can collect the data of all the students across all the universities of the computer science discipline, which is impossible. So you won't do that. So what you will do is you will collect the data from a sample of 100 students. Okay, so you will create a random sample data set from, you will conduct a survey going to about, you can say, let's say a couple of universities. You will interview or give out survey forms to 100 students, and then you will record their feedback and come back, enter that information into the computer, and then perform the different statistical operations they are. So when we were discussing about the random sample data set, what we meant was whenever we are collecting the data from the bigger population, we have to make sure that it is random. And if it is not random, there is another concept that will be introduced in that data, which is called the bias. The bias, as the name states, the English meaning, it's like we are giving a certain favor towards a particular factor, which would alter and disrupt our data, and it will ultimately disrupt our study. So a good example of this would be, if you want to conduct that survey of 100 students, you have to make sure that there is no factor that is being overlooked and there is no factor that is being not constant. So you have to keep all the factors constant, and then you have to study one particular variable. For example, let's say you collect students, data of different students. You're not factoring the information of the financial background of the students. You're not factoring the type of university they're studying in, the type of course they are. So you have to keep all those things constant. If you're conducting a survey, you have to say, okay, I'm going to go to one of the top universities, then I'm going to somewhat middle ranking university, and then so on and so forth. And regarding demographics, if you want to conduct a survey in different states, let's say you have to pick a particular state and you find out that, okay, this state is towards the northwest and demographics are having an effect on your statistics and they're somehow causing a bias in your data. So you have to make sure of that as well. So it's highly likely whenever you're conducting a survey, a bias is introduced into your data set. So how statisticians overcome that is that they already have reference models for it. Whenever they're collecting data, after they've collected it, they visualize it, like in this figure, they visualize it with the reference model. If the collected data is somehow deviating from the reference model, they say that there is a certain bias and they have to study it, what is actually causing the bias. Mostly it's because one of the factors they haven't considered or they haven't been careful enough to make a random choice when they were collecting the data. Okay, so let's talk about distributions. Coming to the formal definition, a distribution is a function that shows possible values for a variable and the frequency of their occurrence. So we're generally going to divide the distributions into two main categories: discrete distributions and continuous distributions. As we have already studied in descriptive statistics, the different types of data variables there were. And we're going to extend those concepts over here as well. So discrete has the same concept as the discrete variable, and continuous has the same concept as the continuous variable. These different types of distributions will model different types of variables. In this course, we're going to study three types of distributions: uniform distribution and binomial distribution. By the shape, you should be able to at least guess that we are talking about discrete distributions because they are bar plots, and bar plots are used to plot discrete variables. So we'll be working on discrete distributions. The uniform and binomial distribution come under the category of discrete distribution. Secondly, we're going to discuss normal distribution, which is a type of continuous distribution, and it is going to model continuous variables. So coming to discrete distributions, we're going to study an example which would be the rolling dice example. In the rolling dice example, there we have a probability. We are going to calculate the probability of a particular occurrence of an event. So the x over here would be our discrete random variable. So whenever you get a problem, you have to think intuitively, and you have to, just before applying all the mathematical concept, you have to take a moment and think what we're dealing with here. So it is a rolling dice problem and the number of dice, and we are calculating the probability of the occurrence of one of the faces on a dice, right? So you know the values on the faces are discrete values. So the next step would be, if you want to calculate the probability of a discrete variable, we would be going towards discrete distributions. So that's how you analytically approach a problem. So the new concept over here is the word of random. We're not calling it discrete variable, we're calling it a discrete random variable. The reason we're calling it that is because this event has no external factor controlling it, right? It is the occurrence of any faces on the dice is entirely up to chance. It's entirely random. If it is a fair dice, if it is not being altered and the whole the game and the event is fair, then this variable would be a random variable because the choice or the value that's going to occur in it will be based on completely randomness and chance. So we have a certain sample space whenever we're going to model any distribution. So the sample space we're going to, for this particular problem, will have the number of values that can occur, the number of values that are on the dice. So 1, 2, 3, 4, 5, 6, they're all discrete variables, and the sample size of this space would be 6. So we're going to calculate the probability, and we're going to display the probability distribution of this particular example. So when we make the probability distribution table, we're going to write down the values of each event, the value of x in an independent event, and we're going to calculate the probability of every value of x. In this particular case, in the rolling dice example, each and every value of x has an equal chance of occurring. As you can see, the probability is also the same of all the different values of x. So when we plot the distribution, when we visualize the distribution, it would be forming a shape of a uniform distribution. So this discrete probability distribution is a uniform distribution type because the probability of all the events is same. But there is another example that we will be talking about that is also a discrete distribution, is the rolling dice example. In this example, we're going to talk about 2 dice rolls. Each dice roll, we're going to roll 2 dice, and we're going to record the occurrence of each value on each dice, and we're going to make pairs, and we're going to record all the values. So the sample space is almost double, and this is the sample space. We have written all the different examples over here. And so the sample space is almost double because we're modeling 2 different dice. So the sample space would be 36. And the discrete distribution, now we have the discrete random variable here is the sum of the 2 dice. Previously we were just modeling 1 dice, and the random variable x only showed the occurrence of a particular face on the dice, the number, and now this time we're actually going to calculate the sum on the two dice. So we just do the same process. We calculate the sum of every event, the possible sum of every event, and we go from the minimum sum would be 2, because the minimum value on both the dice would be 1 and 1, and then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and the maximum value would be 12. So when we, after doing this, after calculating all this information, when we visualize the distribution, it forms the binomial distribution. The binomial distribution is where the value of x, that is 7, which will have the highest probability, is when the sum of the both dice is 7. So as you can see, the probability of x where it is 7 is very high as compared to the other probabilities. Remember, this is also a discrete distribution, and under that category we're talking about the binomial distribution. The word binomial distribution also comes from the bi word, is where we are factoring two variables, two random discrete variables in one particular event. So moving on, let's talk about continuous distributions. A continuous distribution displays the range of probabilities for the outcomes of a continuous random variable. Before we were talking about discrete random variables, now we're going to talk about continuous random variables. And the type we're going to discuss, the type of distribution we're going to see and study, is the normal distribution. So the normal distribution has a number of characteristics. First of all, it is also known as the Gaussian distribution. Secondly, it forms a bell curve. As you can see in the figure, it is forming a bell type structure. And thirdly, and most importantly, which will ultimately help you to extract a lot of information and infer, as we will see later on, we're going to infer a lot of solutions from the random dataset and apply it on the population dataset, is the characteristic of mean, median, and mode. So in a normal distribution, the mean, median, and mode are equal. There is another type of information that can be extracted, that is the standard deviation, which is seen over here as the distance from the mean towards the extreme right value of the figure. So the normal distribution is denoted mathematically by this particular notation. It's basically mathematical, and whenever you will write it down, it is this notation will be followed. So let's talk about a normal density function with different means. It's pretty obvious and intuitive. I won't go into complete detail. If you just have, by looking at the figure, you can see that if the middle value, if the peak of this bell curve, the x value where there is the peak of this bell curve shows the mean. So whenever I'm moving the mean over on the x-axis, the overall curve will also move. Regardless, it will not change the overall shape. It will not get stretched. It will only get shifted towards right or left, depending on whether I'm increasing or decreasing the mean. The same concept applies to the variance. Like I said, the distance between the mean and towards the extreme right, the line over here, shows the standard deviation, which can also be referred as to the variance if I square it. So if I increase or decrease it, the graph would basically stretch out if I increase it, and it would become less spread out when I decrease it, and its height would also increase. So the value of y would also increase. So this is the different types of sigmas on which the bell curve would change its figure. So let's talk about standard normal distribution. Standard normal distribution is a type of distribution in which we make the mean 0 and standard deviation 1. And how we do that is we actually subtract the x value with its mean and divide it by the standard deviation. So then we get another value which is called the z-score. So in this way we will standardize a normal distribution which already we have. The essence of calculating the z-score is that it will tell us how much the score is above the mean value. So it will tell us whether how much the z-score is above or below the mean, and it will give us it will answer us a lot of questions in which we have to do with the relative standing of a particular value in the dataset. So it is basically used when we are calculating the probability of a data point occurring on a normal distribution curve, and it helps compare two scores from different normal distribution. So when you have two different normal distributions and you have to compare two data sets, so you draw the two different normal distributions and you have to compare them, you have to first standardize them. So in the process that now you have both of those normal distributions have the same mean and the same standard deviation, so that now we have kept all the other factors constant. Now we can compare them on one reference value, that would be the z-score.